Hello, Engineering Statics, ENGR ampersand 214 students. This is a quick example problem in particle equilibrium. So as a quick reminder, particle equilibrium requires that the sum of the forces in all three orthogonal directions sums to zero, which gives us a net force on a particle that's zero. So F equals ma is zero, so our acceleration is zero, and we are in static equilibrium. So for this particular problem, we've got a small ball, and it is small enough that we can consider it to be a particle. So particle equilibrium applies. It's got some mass, and so the gravitational acceleration gives it a weight of 20 newtons, and it's being held up by one spring, and it's being constrained horizontally by another spring. And it's also being pulled downwards and to the right by a really thin cable, like maybe a thread, something pretty thin and of limited tensile strength. And we're told that the max cable tension is 5 newtons. So that's the most force that cable can apply without breaking. And so we're basically told that assume that the cable is carrying as much tension as it can. It's applying its full 5 newtons. And these two springs are at right angles, to the vertical and the horizontal in their stretched state. So the ball has some weight, it's stretched both springs, and they're still pretty much horizontally and vertically oriented. The ball is being held by this very weak thread, and somebody wants to know how far did the springs each stretch, and we have a spring constant in each case. So the spring constants are different, so and we don't know what forces they've exerted, so it's pretty reasonable that we can assume that the delta x for each one is different. So delta x being, I guess maybe we should call it delta y in one case, but we'll call x in this case the spring extension. We're going to assume they're different. We have no reason to think they'd be the same, so we'll assume they're different. So this gives us unknown number 1 and unknown number 2. There's two different things that we don't know that we would like to know. We know that we've achieved static equilibrium. So that means, and we have a 2D scenario. We don't have any forces in the third dimension coming into or out of the board, the screen. So we have 2D. So we know we have two equations that we can use to try to solve for our unknowns. We're going to have an expression for the sum of the forces in the x direction and the y direction. We have two equations, and we have two things we don't know. So we've got a good chance at being able to solve for those two things. And the other thing that we're going to need, that I'll just write up here maybe in green, is, if people don't remember from physics, the force that a spring exerts, either pushing you or pulling you, is the spring constant times the extension or compression of the spring. So we were given this in both cases, and so these are our unknowns, UK meaning unknown, not referring to Great Britain in any way. So if we could represent the spring forces with a number based on things that we already know elsewise, given that we have K, we can solve for our extension in both cases. So how far did each of the springs stretch? And they're probably, given that everything else is in tension, they're stretched, not compressed. So let's go ahead and FBD it. We got a schematic, but we could miss something. So we're going to FBD the ball. FBD meaning free body diagram. We're going to construct a free body diagram. I often turn free body diagram into a verb just because it is so imperative in solving statics problems that it ought to be given verb status. But that's a bit of slang on my part. It is a free body diagram. That's a noun, but we will draw a free body diagram around the particle. We can draw a free body diagram of anything that we want, but it's most useful to draw it of the particle. So I'm going to draw a little blue cut line. I'm going to cut that particle out. I'm going to free it up. I'm going to free it from its contacts, and I'm going to represent the action of those contacts and gravity with a force. And I'm going to draw the forces in green. So I know that the little ball has some mass, and that results in a weight force of 20 newtons. I know that it's being pulled on by a cable, which I'm told is pulling at its max tension of 5 newtons, and I know that that angle there is 45 degrees to the vertical. It's being yanked upwards by the force coming from spring 1, F spring number 1, and it's being yanked to the left by F spring number 2. One of the things I'll note that simplified all of this is, again, we've got, that's a 2 there, we've got a cable. Cables can't push, they can only pull. So by telling us that this was a cable and giving us the max tension and saying it was exerting the max tension, we automatically had a magnitude and a direction for this force. We knew that it was at 45 degrees to the vertical because we were shown that in our geometric sketch. We were told it's pulling with it's exerting 5 newtons, and because it's a cable, it is pulling, not pushing, with 5 newtons. So we got the full magnitude, orientation, direction of this one force vector from that language in the problem. Okay, so this is our FBD of the ball, and the ball is small, and so it's acting like a particle. So if I wanted to put some coordinate axes down on the ball, and I put the ball right at the origin, and I'm going to put j hat going up, and that's the positive y direction, and I'm going to put positive x direction over to the right, which is kind of the standard way that I'm used to. Now I'll go ahead and start tallying up my forces in the x and y direction. So I'll start with the x direction. I'm going to write an expression for the sum of the forces, all the forces in the x. So I'll start with our tension force. We've got part of it, and it's going in the positive, so I have 5 newtons times cosine 45. I could have said sine 45 because it's the same in this case. And the weight's only pulling down, spring 1's only pulling up, spring 2 is pulling in the negative x direction. We'll just call that FS2, meaning spring 2. And that has to sum to 0. All right. This is going to give us our spring 2 extension directly. That's a real help to us. So everybody grab your calculator. So I can say 45 cosine is about 0.0707 minus spring constant 2 times spring extension 2, which is one of the things I wanted to know. And that is 20,000 newtons per meter. So 0.707, or sine or cosine of 45 times 5 gives us about 3.536 newtons. I'm trying not to round off too much in the middle of calculations since that's super bad practice, but I'm keeping all the numbers in my calculator, and you should do the same thing. Only round off at the end. And I will admit I'm not being ultra picky about my significant figures here. Obviously, if this were for real, I would go grab the least significant figure of all of my input data, and then I would round or truncate my final answer according to that. So I can do a little bit of algebra and get an expression for delta x2 is equal to 3.536, and this is again the stretch in spring 2, divided by 20,000 newtons per meter. The newtons cancel, and I get a 3.5355 20 1 2 3 20,000 divide, and so I should get about 1.77 times 10 to the minus 4 meters. So about 0.2 of a millimeter of stretch. So not very much. For those of you who are going on to mechanics of materials, that's a small displacement. So if this had been a statically indeterminate system, you could solve that. So very, very little stretch from maybe when we release the spring to now. But this is statics. We only care about the static position, so that's spring. So we can just go with the geometry we have. Spring 2, stretch. So there's one. So we have another equation of equilibrium available to us that we'll hope will give us our stretch in the vertical spring in spring 1. So let's tally up all of our forces in the y direction, and again I'm going to be looking not to my schematic, but I'm going to look over here at my FBD. I used my schematic to get my FBD. I draw the data from my equations of equilibrium from the FBD. That's what it's there for, to do for me. Okay, well let's start in the positive direction. We have F spring 1. We'll call it FS1. None of the spring force 2 is in the y direction. It's pointing totally horizontally. We have 20 newtons in the downward direction from the weight of the ball, and we have 5 newtons times sine theta or cosine theta. Ooh, not 50 newtons. 5 newtons sine theta in the downward direction. So let's check, did we get them all? F spring 1 going up, weight going down, and a portion of the 5 newtons going down equals 0. So this is a number that I know. That's 45 degrees. I know that number, and the force of spring 1, I'll be able to solve for that, which will give me my, since I have K1, I'll be able to get my stretch of spring 1. So we can do some algebra and get an expression for force of spring 1 is going to be equal to 45 sine 5 newtons times 20, my calculator's not responding, 20 plus, so that's going to be 23.5, call it 54 newtons, and that's going to be my stretch times my spring constant, (10,000 newtons per meter). So I can solve for a stretch. So I just divide my 23.5 for newtons divided by 10,000, and I get quite a bit more, a couple of millimeters, a bit more than 2 millimeters. So I was able to calculate how far each of these springs stretched by knowing something about springs. I had to know that. And then once I did, I was able to solve for those spring forces using my equations of equilibrium. I had all the other data I needed, so I ended up with basically only 2 unknowns. And I had 2 equations because I knew I was in static equilibrium and I was 2D, so I had 2 equations. So I was able to solve for my 2 unknown forces, which put together with what I knew about springs gave me what I was asked for. So this is another example of how to use particle equilibrium to solve for unknowns about a system of forces. And that is it for this example.